welcome to our class. So in the last classes we have discussed about the Metal-carbene based catalyst for olefin polymerization, and we have discussed very thoroughly about the mechanism and most interestingly that how the symmetry dictates the stereoregularity in polymers where you will be using the two-chiral monomer as example propylene. And we saw that several advantageous factors upon the Ziegler-Natta catalyst, and we have now very good knowledge about the Metal-carbene based catalysts. So today we will try to discuss that how the Metal-carbene catalysts from the Metal-carbene catalyst, how the recent development of the post-metallocene based catalysts have been done by various groups, not only for academic interest and also for the industrial importance. So we will discuss what is the need. We had already very good catalyst, Ziegler-Natta catalyst, then Metal-carbene, the Cummins-Kiss type catalyst. Then what is the need of developing the post-metallocene based catalyst? So that we will try to discuss, and also we will try to discuss with emphasizing its chemical structure, design, and the mechanism, and what is the advantageous output. Okay. So in this class we will try to learn what are the post-metallocene catalyst, okay, and what the design and chemical structure associated with it, what are the basic criteria of the ligands and also the metals. Then we will discuss its polymerization and reactivity, and obviously the advantageous factors upon the well developed and industrially accepted Metal-carbene based catalysts, which are Cummins-Kiss type catalysts. Okay, so these are the key points. Constant, we learn constant geometry, okay, non-metallation. So let's start. So far, as I told just a few minutes back, that now we are very familiar with this kind of Metal-carbene catalyst, where you have metal is basically the titanium or zirconium, and these are plus 4 oxidation state, and you see here different bridging units will be there. This is basically the category of ANSA cyclopentadienyl Metal-carbene complexes, and this X is a bridging, and this bridging, you know that we have now a very good idea that how the bridging units affects its reactivity, the chemical structure, and also the stereoregularity and activity. So we now have a very good concept about the Metal-carbene catalysts, and we have now learned that how that symmetry is related with the stereoselectivity, and which is the main beauty of this kind of Metal-carbene catalyst. So depending upon the symmetry of the Metal-carbene initiator, you will be getting the respective tacticity in the polymers. And not only that one, the activity also you can change by changing the bridging unit, by changing the substituents on the cyclopentadienyl, and obviously using the co-catalyst, because here you will see that this catalyst is not active catalyst. Okay, we learned it. Okay, this is not active. You have to do the activation. So this is the activation of the catalyst which we use MAU or the boron based that we have discussed in the last classes, and then it undergoes the insertion reactions, alkene coordination followed by insertion, and then we get the respective polymer unit here you see. Okay, and also we have learned that depending on the polymer symmetry, we will get the different tacticity. So as example, if you remember, if you have C2 symmetry, then we will get the isotactic. Okay, then if you have a CS symmetry, then we will get the syndotactic, and if we get the CS meso, we will be getting the atactic, So that we have now learned. Okay. So and very pictorially I will show you, okay, that if you have a C2 symmetry, then why we will get the isotacticity. So that is so you can assume that this one I am just doing in a very cartoon, using a cartoon diagram, so that you can easily understand. So this is, say, is a metal center, okay, and this is my back-end site, that is the active sites actually, okay, where the polymerization growth will be happening and the alkene coordination will happen, okay, that is the monomer coordination. And these are my the CP rings, okay. So I will, let's say this is the one CP ring and this is the one CP ring, okay. Now you will see here in this case, okay, this is the one another C2 symmetry. Now if it is CS, then what will happen, okay, although in the last class we have discussed with all the symmetry axis. So here again these are the active site, okay, and these are the one CP ligands, and in a cartoon diagram, and this is the another CP ligands, okay. This is definitely is a fused CP ligands. It may be the, let's say, indenyl, another may be CP rings, okay. And this case, this is this one, and then another one like, let's say, C1. So what will be the scenario? So again, let's say this is my metal and this is my back-end site, that is actually the active sites for the polymerization, and let's say this is my one ligand and this is the another ligand, but this is not symmetric. So like put like another substituents or another aryl or alkyl. So now you try to understand that what is here, okay. So you will see here, this is obviously the homotopic, that is this binding site and this binding site. If you see the symmetry, that is the homotopic binding site, homotopic binding sites, okay. And for the next one, this is this one and this one is enantiotopic, binding sites, okay, and this one and this one is diastereotopic, okay. And in the last classes we have discussed in depth using the symmetry axis and symmetry operation, and we now know that how the active sites differs by changing the symmetry of the metallocene units and what are the output. So output will be the different tacticity in the polymers if you take as one prochiral monomer, as example propylene. So that we have learned, and these are the most advantageous factors of the metallocene based catalysts, okay. So we can very nicely control the stereoregularity in the polymers, okay. So that is the most beautiful factor in the metallocene based catalysts, okay, fine. So however, one thing we have to understand that if your CP ligands are not bridged, then due to the fast rotation of the CP ligands, CP rings, we don't get any kind of tacticity. It is very difficult to get the a particular tacticity in the polymer. So as example, like this one, okay. So here, so you see that this one, and this one. So with the same composition of this ZR, okay, indenyl 2 and X2, this one, you will see that it can exist in the three conformants. One is the enantiomeric RNS, that is the resting, racemic, and another one is the meso. So R and S, that is the racemic mixture, will give the isotactic polymers, and the other one will give the atactic polymers that we know now, okay, and we now can explain why we get it. However, it is very difficult to control the tacticity using this kind of ligands if you don't have the bridging unit. In this case, it is easy because it is, you see, this is the bridging. That means there is some restriction in the rotation. So, unbridged metallocene has rarely gives stereoregularity. Okay. However, we can do it by designing the ligands in a very judicious way. What we have to do? We have to basically increase the barrier energy. So, suppose in this case, if you see this one, what is there? There is a phenyl group. Okay. Now, in this scenario, what will happen? There is a sufficient barrier, energy barrier between this one and this one. And due to this one, what will happen? There is the lifetime of the anti. So, this is, you see, this is the anti-conformer. This is also anti-conformer because this phenyl group and phenyl group is in anti. Okay, here. Now, this is basically enantiomer of, this is the pair of enantiomer. These are because these are it's a relation of mirror image relation is there, and this is a meso type of conformer. Okay, you will see that this is the plane of symmetry is there. So, this is a meso type of conformer. Now, if the barrier is energy is sufficient or more than the alkene insertion, okay, so that means if lifetime is more than the alkene insertion, then what will happen? We can have a sufficient time to get that particular conformer or to react with the prochiral monomer. And then what will be the effect? Effect will be that you can get a stereo block copolymers. Okay, and that is important. I will discuss in the last slide what is the stereo block copolymers and what is the importance. So, this kind of molecules called the fluxional molecules. Fluxional molecules. That means that conformationally dynamic. Okay, mainly dynamic. So, it can exist in different conformers, but with sufficient lifetime. Okay. So, in this case, what is the barrier? Sufficient barrier between conformers. Okay. So, that, and what will be the result? The result will be that it can provide the different stereo polymers with the same metallocene catalyst, and sometimes it is advantageous. Okay. I will give one example and you will understand then why it is advantageous. So, it can play the role of two catalysts. So, single catalyst, dual role. Okay, we no need to use the two catalysts. So, here you try to understand these two type of. So, we now know that isotactic polymers, syndiotactic polymers, propylene, okay, or atactic propylene. So, that we know what is this. Here I have used one term, hemi-isotactic polymers. Hemi-isotactic polymers means that here in all the polymer chain, in the polymer, throughout the polymer chain, there will be that methyl group in a particular configuration, and the adjacent methyl group will have the random. As example, one, let's say one is the R, that will be adjacent R or S, like that, randomly. There will be no order. But in the stereo block propylene, you know that block copolymers we have discussed in the beginning. So this is, you see that this is a block. So here it will, what will happen, here will be the same a particular configure, that methyl will be, and the other block will have a same but different. That means if it is isotactic, then this will be syndiotactic, sorry, this will be atactic or syndiotactic. So one block fully contain the isotactic, and the other block is either atactic or the syndiotactic. Then in this scenario, we will call the stereo block polypropylene. So that's why I have written here, in one block same a particular, and other one same but different configuration. So this is called the stereo block copolymers. Okay. Now here you see that this is very interesting. Okay. So if you use this catalyst, this is, you see, without bead. Okay, without bead. Okay, and as the barrier between the two conformer is quite good, that's why it can exist, and the lifetime is sufficient enough to react with the alkene, prochiral monomer. So now what will happen, you can get the stereo block propylene using this catalyst. So you no need to use two catalysts, single catalyst is enough. Okay, and stereo block polymers is interesting for some applications, because this one is actually can be used as a thermoplastic elastomer. Okay, because you know that isotactic block, it has an isotactic block. This block is actually crystalline. Okay, and this crystalline block actually acts as a physical cross-linking domain. Okay, so that's why sometimes we also are interested for the stereo block propylene, where one block will be a particular stereoregularity and other block will have a different, but the different stereoregularity. So and you can make using this kind of catalyst with a properly designed, okay, Metal-carbene catalyst. So this is one beautiful example of for such applications. So I'll just discuss in little depth about this stereo block copolymers using the oscillating Metal-carbene based catalyst. So this is also called the oscillating Metal-carbenes, because it oscillates between the anticonformer, then mesoconformer, and the other anticonformer. Okay. So suppose I am doing the polymerization with this catalyst, okay, and it exists in the solution in three conformers. Okay, and I am using the monomer, that is the propylene. Let's see, okay, what kind of stereoregularity we will get. So let's take a small chain of the polymer, and we will try to understand that what are the tacticity we can get it. Okay, so let's say take a small chain, and let's try to understand by using this line diagram. Okay, so okay, fine. So this is the case 1, okay. I am writing, I will explain what I am doing, and this is the case 2, okay. So 1, 2, 3, 4, okay. Now you label it. So we have learned this in our previous classes. So this is M, this is R. So this will be again M, 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 R, M, M. So here also M, M, M. This will be R, this will be R. Then again M, 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 M. Okay. Now you will see that there is basically this is the enantiomer, this is the enantiomer. So if we consider that this is the A form and this is the B form, and this is basically you can say plus minus A. So basically actually it contains the two species. One is the equilibrium between plus minus A and the B. Okay, B is the meso. So we discussed in the last classes that whether it is a two enantiomer, but eventually it will give the isotactic polymers, whether it is the plus isomers enantiomer or minus enantiomer. Okay. So now you see that there is a 3 equilibrium between this one. So equilibrium may be 2 possibilities, this one or plus A minus A. So we will try to understand that what are the dominating equilibrium, whether this one or whether this one. So that means what are the species actually present mostly and who are the responsible for the polymerization. Now you will see here, if it is in this case 1, so you will see that M, 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 M and then M. So that means okay, that this one is this is the error. So here this is the error and here this is the error. Okay. So what you are getting, basically you see that you are getting the M, 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 then there is a one error, then again you are getting M, M, M. Okay. Then if there is another error, then again you are getting M, M, M. That means obviously that it will be, this polymerization is by the plus minus A. Okay. That means the enantiomer, not by the meso, but because meso has no chiral environment. Okay. So this one definitely by the chiral catalyst, and this one, so this is the error and this is the error. Okay. So here you will see that this is R and again this is the R. So that means you will see that this error is due to the meso isomers, that is the achiral. See, this error is due to meso isomer. Okay. But in the experimentally it has been observed that case 1 is the dominating. That means you will get the case 1 in major. Okay. So it proves that mostly in solution the equilibrium, the major species is basically the racemic, the plus minus A. So that is the so from this experiment, and you can do it by simple proton NMR C13 spectra. You can by the concept of the dyads and triads, you can calculate that how much the tacticity is there and how much and what are the errors are there, and depending on that one you can tell that whether this polymerization has been done by the catalyst site control or chain end control, or whether by the chiral environment of the catalyst or by the achiral catalyst, and this way you can judge that who are the responsible or active species in this polymerization. Okay, by this observation, we can tell that most of the majority active species are the racemic. Okay. So there is a equilibrium between plus minus A. This one is the major equilibrium, not the plus minus A and B, between B. Okay. So this is really very good information, and it is very helpful to make the stereoregular copolymers. Okay, fine. Now today we will introduce a different type of catalysts, that is the post-metallocene catalysts. So the name suggests that post-metallocene, that means ahead of the metallocene. So something will be definitely, we are either modifying or replacing or doing some extra design of the catalyst. So what are they? Okay. So here you will see some of the examples. This is the very famous catalyst, that is the Dow's CGC catalyst. That CGC means we will discuss. That is the constant geometry catalyst. Okay, the CGC catalyst. And other one is the Nova catalyst, that is also very famous, and in all the cases you will see that one CP is missing. Okay, so one CP ring is there and other CP ring has been replaced by the amine or imido type of ligands. Okay, and one CP is replaced by immunoligand. Okay. So and others are as usual. Okay, whether the titanium or zirconium. So these are specifically, these are very effective and famous catalysts. That's why I am discussing with these two examples. And these are you can see basically half sandwich complex, very easy to understand. In other complex you will see there is two metallocene. Okay, and here one metallocene is gone, so that's why the half sandwich complex. And it's a more open, because you see steric hindrance is less. Okay, less steric hindrance here at this site. Okay, so that's why the more open in nature. That means here, so this side is more open, and that's why the monomer can approach. And but however, there is another disadvantage. The activity is very high, because there is a lot of space, monomer can easily come, there is less steric hindrance, but we have to sacrifice the stereoregularity. Okay, so we discuss what is the reason. So but these are perfect for ultra high molecular weight polyethylene, that is the advantage. Okay, and also you can get some branching using the copolymerization. We will discuss what is the copolymerization. So we can make high molecular weight polyethylene. We can make the LLDP, that is the linear low density polyethylene. Okay, using the copolymerization. So instead ethylene and another alpha olefin, as example hexene, butane, like that. Okay, because as it is a more open, that means it can little sterically hindered alkene or longer chain of alkene also can coordinate very nicely. Even not only the alkenes, it can also can coordinate like a styrene. So it can polymerize the styrene molecules. It can also norbornene. Okay, you can understand that so much sterically hindered monomers also can be polymerized by this kind of catalyst. Okay, so but as I told that stereoregularity is a issue, and you will have a less stereoregularity. And as example, like if we quantify this kind of ligands, will give the maximum of 0.7 ratio of the MMMM, that is the this one is basically quantifies the how much stereoregularity is there. So that we have to sacrifice, and with the same condition, if you take any achiral metallocene catalyst, that stereoregularity will be much higher. In that case, the MMMM fraction will be more than 0.9 or something like that. So that is the one disadvantage, but this is the reactivity wise, this is much more than the normal metallocene compounds. Okay. So what are the constant geometry? So this is the why, because you will see that these CP rings, this is the CP rings, okay, and this the titanium, and this one is actually very short bridging. So this due to the short bridging, this is very constant. Okay, this is very constant, and that's why the name is constant geometry. And due to this constant, this space is quite open. So different type of ligands are possible and has been developed with different catalysts of this kind of category, that is the constant geometry. And you will see here that the bridging is maybe the silicon based, carbon based, or multiple carbon based, or the phosphine or boron. Okay, but as I told, generally these are short bridge, not quite longer. Here this X may be oxygen, maybe sulfur based donor, or maybe carbon based donor, and mostly actually is the nitrogen based donor, the imino, okay, substituted imino. And here these CP rings, not only CP, the varieties of substituted CP, okay, you will see here that this one, the indenyl, okay, or fluorinyl, the different cyclopentadienyl or fused cyclopentadienyl are possible, and the metal centers are titanium, zirconium, hafnium, and these are obviously the alkyl or the halides. Okay, and the advantage are lots, as I discussed, that is improved stabilities. Okay, these are quite stable than the zirconation metallocene compounds. So that is really good and more economic. Increased incorporation rates of higher olefin in copolymerization with ethylene. So that why? Because as it is more open in open, so that means when you do the copolymerization with ethylene using other comonomer, as example hexene, butene, or heptene, okay, then the copolymerization rate will be much better, and you will get the LLDP polymer. Okay, so that is okay. So and obviously the higher reactivity towards alpha olefin than Ziegler-Natta catalyst, and that's why it is used for copolymerization, particularly for the linear low density polyethylene, and also like for branched polyethylene. Okay, sometimes we purposely need the branched polyethylene, as we discussed in the previous classes, that property depends on the chemical structure of the polymer, and depending on the property the applications we are targeting for, and that's why we have to design our polymer. We have to take the appropriate catalyst, otherwise we will not get the particular polymer we are targeting for. So you will see there is a huge scope and huge possibilities using different ligands, different spacers, different bridges, and like that. Okay, so in this case you see that the synthesis is very straightforward. Okay, you will see that multiple methods or strategies you can follow. One example, you see that you start from again the CP rings or substituted CP rings, okay, and then you use the butyl lithium and okay, and then the excess SiMe2Cl2. Okay, so here you have a H, okay, and you use n-butyl lithium, then it will be deprotonated, and use XL dimethyl dichlorosilane, then you get this SiCl, that is very labile, okay, and then you react with this one, then you get this compound, that is the template approach, and then you then finally react with TiCl4, then you will get this one, okay. This is called the template approach. The other one, you will see, you start from here, then you use the 2 equivalent of amine, okay, with what amine we are, that is depending on you, that what donor you will be selecting, and then you are use the n-butyl lithium to deprotonate this amine, okay, and then you have N minus, okay, and then you use the precursor like MX4, that is the Z-Cl4 or TiCl4, then you will get your catalyst. So this is called the metathesis approach, because we are exchanging the metals of the lithium by the titanium or zirconium. And one is the metallation approach. Here you will see, you will get that this one, and then you are using the dimethyl amino tetrakis dimethyl amino titanium or zirconium, and you will get the direct metallation. So here you will see three strategy. So strategy 1, strategy 2, and strategy 3, okay. So sometimes it depends on the substituents, depends on the acidity of the involved proton attached with the amine, and also depends on the substituents on the CP rings. So these three methods are generally followed to synthesize this kind of constant geometry catalyst, okay. Fine. So so today we will discuss that how we are approaching from metallocene catalyst to the post-metallocene catalyst, and here we saw that one CP ring has been replaced by the other donors, as example imido or imino, okay, and then we saw that some advantageous properties, that is the mainly the reactivity and getting the high molecular weight polymers. So we are trying to explore the catalytic properties to have our desired polymer. So in the next class we will continue our discussion on the post-metallocene catalyst and its development, and obviously the mechanism, and then we will try to understand the advantageous factors upon the Ziegler-Natta and also the Kaminsky type metallocene based catalyst, okay. So thank you, and see you again in the next class.